Imagine a world long past, a time when the very earth beneath our feet and the flowing waters around us were not just natural elements, but powerful, strategic tools of war. Forget the cannons and muskets for a moment, and picture an age where an entire landscape could be weaponized, where natural features like majestic rivers transformed from mere obstacles into formidable instruments of destruction, defense, and dominance. It's a history largely overlooked, hidden beneath the surface of grand battles and legendary knights, but it's a story of profound ingenuity and strategic brilliance. Today, we're diving deep into the captivating world of warfare by water, how engineers turned rivers into medieval weapons. This isn't just about moats and castles, it's about a revolutionary way of thinking, a testament to human innovation born from necessity and a desperate fight for survival. This journey will reveal the ingenious, sometimes brutally effective, strategies that medieval minds concocted to harness the raw, untamed power of hydrology for military advantage. They didn't have modern machinery or sophisticated algorithms, yet they engineered feats that reshaped battlefields, dictated the fates of cities, and decided the outcomes of sieges. From diverting entire rivers to create impassable swamps to using water to starve out an enemy, these ancient engineers, often unsung heroes of their time, understood something fundamental. Control over water meant control over life itself. Their foresight didn't merely influence the course of medieval history. Its echoes, profound and undeniable, continue to resonate in modern strategic thinking, proving that innovation in warfare is as old as civilization itself, perpetually adapting to the available tools and environment. Prepare to uncover the hidden genius behind these watery fortresses and fluid assaults. We'll explore how these often anonymous figures, with their profound understanding of hydraulics and the natural world, leveraged every ripple, current, and flood to their advantage. Their methods were not just about creating physical barriers, they involved psychological warfare, logistical disruption, and an almost artistic manipulation of the environment. As we navigate through these forgotten tactics, you'll discover that the principles they established, the mastery they displayed over one of nature's most dynamic forces, are far more sophisticated than you might imagine. So settle in, because this is more than a history lesson. It's an immersive exploration into a dimension of medieval warfare that will forever change how you view rivers and the relentless human drive to innovate, even in the face of conflict. Before we fully immerse ourselves in the medieval world of watery weapons, it is crucial to recognize that the strategic importance of water did not simply spring into existence with the building of the first castle. Its genesis, its foundational role in warfare, stretches back much further to the dawn of civilizations themselves. Imagine the Fertile Crescent, where ancient Mesopotamians, thousands of years before the first knights, built intricate irrigation systems to feed their burgeoning cities. These networks, vital for agriculture and survival, represented both a blessing and a profound vulnerability. An enemy didn't need to conquer a city with brute force if they could simply divert its lifeblood, turning lush fields into barren dust and cutting off food supplies. The ability to manipulate these systems to either sustain or starve was perhaps the earliest form of hydrological warfare, a silent yet devastating weapon. Consider the mighty Roman Empire, whose engineering prowess is still admired today. Their aqueducts, marvels of ancient technology, brought fresh water from distant springs directly into their bustling cities, hospitals, and bathhouses. This constant, reliable supply was a cornerstone of Roman life and hygiene. But what happens when that lifeline is severed? cutting off an aqueduct could cripple a city without a single arrow being fired. Roman legions understood this intimately, often targeting enemy water sources during sieges, recognizing that thirst could be a more potent adversary than any army. Conversely, defending their own aqueducts became a critical aspect of city defense, sometimes even incorporating them into the very fortifications. These weren't just feats of civil engineering. They were strategic assets, integral to both offense and defense, laying the groundwork for how future generations would perceive and utilize water in conflict. These ancient precedents illustrate a fundamental truth. Control over water has always been intrinsically linked to power and survival. Whether it was protecting vital irrigation channels in Egypt, where the annual Nile floods dictated life and death, or safeguarding the wells that sustained desert outposts, early societies understood that water was not merely a resource but a strategic domain. They learned to build structures to manage it, to divert it, and to protect it, instinctively recognizing its capacity to be a weapon. These foundational concepts, born out of necessity and honed over millennia, provided the essential knowledge and mindset that medieval engineers would later build upon, transforming localized water control into the far more complex and deliberate systems of hydrological warfare we are about to explore. They inherited a legacy, certainly, but they also innovated on a scale that truly turned rivers into central players on the battlefield. Building on that ancient understanding, medieval engineers perfected one of the most iconic applications of water in warfare, the defensive moat. From the simplest ditches around a stockade to the elaborate, multi-layered water defenses of imposing stone castles and fortified towns, moats became an almost universal feature of medieval strongholds. Imagine a massive, deep channel, often 20 or 30 feet wide and sometimes even 15 feet deep, encircling a formidable castle. This wasn't merely a decorative feature. It transformed a stationary fortification into a virtual island, severing its direct connection to the surrounding land and creating an immediate, impassable barrier for any attacking force. The primary engineering principle behind a defensive moat was deterrence and delay. A wide, water-filled ditch forced attackers to expend significant time and resources simply to reach the castle walls. They couldn't just march up to the base. They had to fill the moat with earth, timber, or debris, or construct temporary bridges, all while under constant bombardment from archers and siege engines within the castle. This process was incredibly labor-intensive and dangerous, making a direct assault far less appealing. Beyond the sheer physical obstacle, the water itself often served to prevent tunneling beneath the walls, a common siege tactic known as sapping, as any attempt to dig would immediately flood the tunnel, collapsing it and drowning the sappers. The effectiveness of these watery defenses depended heavily on their dimensions and, crucially, their water source. While some moats relied on natural springs or rivers that were diverted, many were fed by carefully engineered systems of dams, sluice gates, and even artificial reservoirs. Engineers often designed these systems to allow for rapid filling or draining, giving defenders even greater control. A wide moat, especially one filled with deep water, rendered most siege engines, such as battering rams and siege towers, useless. These massive wooden structures, designed to roll up to the walls, simply couldn't cross the chasm. Ladders were too short, and even if they reached, scaling them while soaked and exposed to arrow fire was a near-suicidal endeavor. The water also served to cushion the impact of projectiles, absorbing some of the force from thrown stones, further protecting the castle's base. The strategic brilliance of the moat lay in its multifaceted defense, creating an almost impenetrable barrier that turned what seemed like a simple ditch into a complex part of a castle's layered defense strategy. Building on the effectiveness of moats, medieval engineers took water manipulation to an even grander scale, developing a tactic known as controlled flooding. This wasn't merely about protecting a single castle. It was about transforming entire landscapes into formidable defensive barriers. Imagine an army, perhaps tens of thousands strong, marching with its heavy siege equipment, supply wagons, and cavalry, only to encounter miles of suddenly submerged farmland, a vast, murky expanse where solid ground once lay. This tactical inundation turned once passable terrain into impassable quagmires, effectively bogging down advancing armies, isolating their siege camps, and disrupting their vital supply lines. It was a strategy that weaponized the very land itself. This strategic use of water was particularly prevalent in regions with abundant waterways and low-lying terrain, such as the Low Countries. Here, a sophisticated network of dikes, canals, and sluice gates, originally built for land reclamation and agriculture, could be rapidly adapted for military defense. By opening specific sluices and breaching minor dikes, engineers could unleash controlled torrents of water, submerging vast tracts of land to a depth that rendered movement almost impossible for an organized army. The water might not be deep enough to drown soldiers, but it was often too deep for cavalry, too deep for wagons, and too soft and muddy for infantry to cross quickly or efficiently. This forced an attacking army to either retreat, find an alternative, often much longer, route, or slowly and painfully wade through the treacherous conditions, making them vulnerable to harassment from lighter, more mobile defending forces. The logistical challenges involved in managing such large-scale water movements were immense and highlight the advanced understanding medieval engineers possessed. It required precise knowledge of hydrology, elevation, and the capacity of various water channels. They had to calculate how much water was needed, where it would come from, and critically, how to drain it once the threat had passed or when agricultural use of the land was needed again. This wasn't simply about opening a gate. It involved coordinating efforts across potentially vast areas, often under the constant threat of enemy interference. The successful execution of controlled flooding could turn an entire region into a defensive asset, a dynamic and ever-changing water-based shield that could halt even the most determined invasion. It transformed the environment itself into an active participant in warfare, far beyond the static defenses of a castle moat. Beyond these grand feats of engineered flooding, medieval ingenuity also focused on seemingly more mundane, yet equally critical, water assets, the humble watermill. While a watermill's primary purpose was to grind grain into flour, a staple food for everyone, their military value often went overlooked. They weren't just about sustenance, they were about power, logistics, and control. For any castle or fortified town, especially one facing a siege, watermills became absolutely indispensable. They provided a consistent, reliable source of food for both the defending garrison and the civilian population sheltering within the walls. Without milled flour, armies could not bake bread, a fundamental component of their diet, and their fighting effectiveness would plummet. Imagine 1,000 soldiers, or perhaps several thousand, needing a steady supply of daily bread to maintain their strength and morale. The ability to produce flour locally, even under siege, was a game changer. This made the watermill not just a convenience, but a critical strategic asset to be fiercely protected. Conversely, for an attacking army, a key objective was often to destroy or incapacitate the enemy's watermills. Cut off the food supply, and you cut off the will to fight. If a besieged force couldn't mill its grain, their stored provisions would quickly run out, forcing them to either surrender or face starvation. An enemy might dispatch raiding parties specifically to burn down a mill, smash its grinding stones, or divert the water channel that powered it. This act of destruction, seemingly minor in the grand scheme of a siege, could have a devastating ripple effect, significantly shortening the duration a stronghold could hold out. It was a form of economic warfare, crippling the enemy without a direct assault. The psychological impact of seeing one's means of sustenance vanish could be profound, eroding hope and accelerating surrender. The continued operation of watermills within a besieged area, however, offered a powerful advantage of self-sufficiency. If a castle or city had access to a reliable water source and its mills remained intact, it could potentially hold out for months, even years, provided it had enough grain. This level of self-sufficiency reduced reliance on vulnerable supply convoys, which were always at risk of interception by the besiegers. Engineers and defenders would go to great lengths to ensure their mills were protected, building fortifications around them, assigning dedicated guards, and even designing them to be resilient against attack. In some cases, mills might even be built within the defensive perimeter of a castle itself, offering maximum protection. The strategic importance of these structures went far beyond their simple function. They were vital nodes in the medieval war machine, symbols of resilience, and silent arbiters of victory or defeat. While the humble watermill played a vital role in sustaining a siege, medieval water warfare extended far beyond static defenses. Rivers, often seen as natural boundaries, were also the lifeblood of communication, commerce, and movement. They served as the strategic highways of their time, providing the fastest and most efficient way to transport goods, troops, and messages across vast distances. For those who mastered them, rivers became powerful instruments of control, enabling both offensive and defensive operations on a grand scale. Control of a river meant control of access, and in an era before widespread paved roads, this was an almost insurmountable advantage. This brings us to the fourth weapon in the medieval arsenal: naval blockades and riverine patrols. Unlike the mighty warships that plied the open seas, riverine fleets were typically composed of smaller, more agile vessels. Picture longboats often propelled by oars for maneuverability in currents, shallow draft barges capable of carrying significant cargo, and even adapted fishing boats or ferries pressed into military service. These were not grand naval battles with towering sails and dozens of cannons. Instead, it was a more intimate, tactical form of warfare, focusing on precise movements, ambushes, and the relentless interdiction of enemy movements. For instance, a fleet of flat-bottomed barges could be chained together to form a floating barrier, effectively creating a blockade that halted all river traffic, cutting off a besieged city or a strategic fort from outside aid. The tactics employed in riverine warfare were as varied as the waterways themselves. Patrols would constantly move along key stretches of a river, watching for enemy supply boats attempting to sneak through or scouting for troop movements. Ambushes were common, with vessels hiding along forested banks or behind islands, ready to spring out and overwhelm unsuspecting enemy convoys. Speed and stealth were often prioritized over heavy armor or weaponry, allowing these fleets to strike quickly and disappear before a larger force could respond. The goal was twofold: to deny the enemy the use of the river while simultaneously ensuring one's own forces could utilize it freely. This often involved building small, fortified outposts along riverbanks, serving as resupply points, watchtowers, and bases for river patrols, extending control far beyond the immediate vicinity of a castle or town. Imagine the frustration of an army trying to supply its forward positions, only to find every river route choked off by enemy patrols, forcing them onto slow, arduous overland journeys. Or consider a besieged city desperately awaiting reinforcements or food, watching helplessly as enemy longboats prevent any relief from reaching them by water. Such blockades weren't just about military strategy, they were about economic strangulation and psychological warfare. By controlling the watery highways, medieval powers could dictate the flow of trade, starve out garrisons, and isolate entire regions, effectively making vast stretches of land their own. This demonstrated a profound understanding of logistics and supply lines, proving that sometimes the most effective weapon isn't a sword or a siege engine, but the absolute control over the vital arteries that sustain an enemy. While controlling the flow of goods and troops on rivers was a powerful tool, medieval engineers also mastered a far more sophisticated and devastating form of water warfare: diversion and deprivation tactics. This wasn't about blocking passage, it was about weaponizing the very essence of life itself. Imagine a city bristling with defenses, its walls impregnable, its garrison well-fed. But what if you could cut off its lifeline, not with a sword or a siege engine, but by simply redirecting a stream? This was the chilling genius of hydraulic siege warfare, where the power of thirst became a weapon capable of forcing surrender without a single direct assault. This strategy often involved intricate feats of engineering. Opposing forces might divert a river or stream that fed a city's wells or filled its moats, leaving defenders parched and vulnerable. Sometimes the goal was even more insidious: to deprive agricultural lands of their vital irrigation. In an agrarian society, cutting off water to crops could lead to widespread famine, crippling an entire region and forcing its inhabitants to abandon their homes or starve. Such tactics weren't just about winning a battle, they were about breaking the will of a people, demonstrating a profound understanding of how to wage war on a systemic level. Consider the psychological toll this would take. Day after day, watching the water levels drop, knowing that every sip taken pushed the city closer to its end. The despair of seeing crops wither and die, understanding that starvation was an inevitable consequence. The enemy didn't need to storm the walls, they just needed to wait. This slow, agonizing pressure could shatter morale faster than any bombardment. For the besieged, it was a constant, gnawing fear, forcing them to make the unthinkable choice between fighting an unwinnable battle and giving up everything they held dear for a chance at survival. Historical accounts hint at these hydraulic sieges, though detailed records are often scarce. One notable example, though slightly later than the strict medieval period, is the Siege of Tyre in 1124 during the Crusades. The Crusaders reportedly attempted to divert mountain springs that supplied the city, though the defenders managed to counter their efforts. Even earlier, ancient Roman and Greek sieges involved similar strategies of cutting off water supplies, demonstrating that the concept of using thirst as a weapon was a long-standing one. These were not quick victories, but long, drawn-out affairs that tested the endurance and resilience of both sides. The attacker needed to maintain their diversion, often under threat of counterattack, while the defender desperately sought new water sources or rationing strategies. The impact wasn't just physical. The sight of a once flowing riverbed turning to dust or once lush fields becoming barren would have been a powerful symbol of the enemy's complete dominance. It was a tangible demonstration of their power to control nature itself, adding a layer of psychological terror to the already desperate situation. These tactics underscore a crucial point about medieval warfare. It was rarely just about brute force. It was a complex dance of strategy, logistics, and a deep understanding of the environment, where the manipulation of something as fundamental as water could determine the fate of kingdoms. It was a stark reminder that even the most well-fortified stronghold was only as strong as its most basic resource. While cutting off a city's water supply was a devastating tactic, medieval warfare in colder climates presented a unique hydrological challenge and opportunity: ice. It wasn't always about actively engineering a frozen landscape, but rather about a deep understanding of ice itself, its unpredictable nature, its strength, and its breaking points. For both defense and attack, recognizing how a frozen river or lake could serve as a pathway or a deadly trap became a critical, often overlooked aspect of strategic planning. Imagine a vast frozen river, seemingly an open invitation for an invading army. However, for the defenders, this could be a deceptive advantage. Knowing the precise areas where the ice was thinnest, perhaps near rapids or warm springs, allowed them to lure enemy forces into precarious situations. A seemingly solid crossing could suddenly become a death trap, plunging heavily armored knights and their horses into the frigid depths. This wasn't merely a natural hazard. It was often a calculated risk, a gamble taken by a cunning commander who understood the nuances of the frozen environment. They might even try to subtly weaken certain sections of the ice, perhaps by cutting narrow channels beneath the surface or by sending light detachments to test its limits, ensuring it would hold for them but not for their unsuspecting opponents. Conversely, for an attacking force, a frozen river offered a potential bypass around heavily fortified bridges or river crossings. A direct assault on a bridge could be suicidal, but if the ice was thick enough, it could support the weight of an entire army, allowing them to approach a fortress from an unexpected direction. This required meticulous reconnaissance, sending out scouts to measure ice thickness and assess its stability, often under the constant threat of enemy patrols or hidden dangers. The success of such a maneuver depended entirely on accurate information and a precise understanding of the local climate. A sudden thaw or an unexpected weight could turn a strategic advantage into a catastrophic defeat. The environmental aspect of this type of water warfare cannot be overstated. Unlike a constructed moat or a diverted stream, the state of the ice was dictated by nature. Commanders had to be acutely aware of weather patterns, temperature fluctuations, and even the subtle sounds of shifting ice. A period of sustained cold could transform a defensive barrier into an offensive highway, while a sudden warming trend could turn a safe passage into an impassable, dangerous expanse. This forced medieval strategists to become amateur meteorologists, constantly observing the sky and feeling the air, for their lives and the lives of their armies often depended on their ability to read the subtle cues of winter. It added an unpredictable, almost magical element to the battlefield, where the very ground beneath their feet could be their greatest ally or their most treacherous enemy. The ability to cross rivers, whether for attack or retreat, stood as a strategic imperative, often as crucial as defending them in medieval warfare. For medieval engineers, overcoming these watery barriers demanded ingenious solutions, leading to the development of sophisticated techniques for bridging. While permanent stone bridges were marvels of their age, they were few and far between, inflexible, and easily sabotaged. The true game changer was the mastery of temporary crossings, particularly pontoon bridges, which transformed rivers from impassable obstacles into vital highways for armies and supplies. Building a pontoon bridge was a complex operation, far removed from simply lashing logs together. It required careful planning, skilled labor, and a deep understanding of river dynamics. The engineers first had to assess the river's width, depth, and current speed. Then they gathered the necessary materials, usually an abundance of timber for the decking and sturdy boats, barges, or even inflatable animal hides for flotation. These buoyant elements, known as pontoons, were spaced out across the river and anchored securely to the riverbed or banks to prevent them from being swept downstream. Strong ropes or chains then connected them, forming a stable foundation upon which wooden planks were laid to create the road for troops and wagons. The speed with which these structures could be assembled was often astonishing, sometimes completed in mere days, allowing an army to maintain its momentum during a campaign. These vital logistical tools revolutionized troop movement, allowing armies to bypass fortified crossings or surprise enemies by appearing where they were least expected. Imagine an army of thousands, complete with cavalry and siege engines, needing to cross a wide, fast-flowing river. Without a pontoon bridge, this would have been a chaotic, perilous, and time-consuming endeavor, forcing them to seek out distant fords or negotiate with local lords for passage. With a quickly deployed pontoon bridge, however, the commander could maintain tactical surprise and operational speed, projecting power across the landscape with unprecedented efficiency. This capability was invaluable for sustaining offensive campaigns, enabling rapid advances into enemy territory, or ensuring a swift, organized retreat if circumstances demanded it. Beyond building new bridges, medieval engineers were also adept at swiftly repairing permanent ones damaged by enemy action or natural disaster. A broken arch or a sabotaged timber deck could halt an entire army, making immediate repairs paramount. This often involved erecting temporary supports, patching damaged sections with readily available materials, or even constructing a bypass using pontoon techniques until more permanent repairs could be made. The speed and resourcefulness of these engineers could literally determine the success or failure of a military campaign, highlighting their often unsung role as vital players in the grand chess game of medieval warfare. Their ability to tame the rivers, however temporarily, ensured that armies could move wherever the strategic situation demanded, transforming the challenging terrain into manageable pathways for power projection. While bridges allowed passage, sometimes the best defense lay in what you could not see, lurking beneath the seemingly calm surface of the water. Medieval engineers were masters of clandestine defensive measures, creating hidden underwater obstacles that were less visible but equally deadly. These submerged traps could turn a seemingly navigable river or a shallow crossing into a death trap for advancing enemies, proving that what you cannot perceive can often be the most dangerous. One of the most insidious forms of these hidden defenses involved sharpened stakes, often made from sturdy timber, driven into the riverbed. These chevaux de frise of the waterways were positioned just below the surface or in tidal areas, designed to become exposed at low tide, impaling the hulls of approaching boats or gashing the legs of wading soldiers. Imagine a seemingly clear river suddenly becoming a minefield of sharpened points as an army attempts a swift crossing, with each step a potential injury or worse. These simple yet effective devices were incredibly difficult to detect, especially in murky waters or at night, making them a terrifying and demoralizing hazard for any force attempting an amphibious assault or riverine penetration. Their effectiveness lay in their surprise and the damage they inflicted, turning the very water into an active participant in the defense. Beyond individual stakes, engineers also deployed sunken chains or heavy nets across waterways. These formidable barriers were often stretched between fortified points on either bank, positioned either just below the surface or designed to be raised quickly from the riverbed via winches or capstans. Their purpose was clear: to snag the keels of enemy vessels, tear their hulls, or entangle their oars, effectively trapping them in a vulnerable position. Once snared, these ships could then be subjected to missile fire from the shore, boarded, or left to flounder. This tactic was particularly effective in narrower rivers or harbor entrances where the enemy had limited room to maneuver, turning the river itself into a choke point that could halt an entire naval force and deny access to vital areas. showcasing an elegant blend of engineering and tactical foresight. Furthermore, medieval defenders were adept at creating debris fields or using natural hazards to their advantage. This might involve felling trees into a river upstream, allowing the current to carry them downstream to accumulate in strategic bottlenecks, forming improvised logjams. These natural obstacles, sometimes reinforced with additional timber or rocks, could create dangerous rapids, disrupt river traffic, or force enemy vessels into predictable channels where they could be more easily targeted. In some instances, the deliberate sinking of old, unneeded boats or barges in precise locations could also form artificial reefs, creating shallow areas or hidden obstructions that would ground larger enemy ships. These methods showcased a deep understanding of the river's power and a willingness to manipulate the environment itself as a weapon, revealing the layered complexities involved in medieval water warfare. These hidden perils transformed the rivers from mere pathways into deadly, unseen battlefields, where every ripple could conceal a threat. Beyond the static, hidden dangers lurking beneath the surface, medieval engineers truly elevated water warfare by understanding and exploiting the dynamic forces of tides and currents. For coastal fortifications or even rivers influenced by the rhythmic pull of the ocean, the ebb and flow of water became a powerful, invisible ally or a formidable enemy. This deep environmental knowledge allowed commanders to time their attacks or defenses with uncanny precision, transforming natural phenomena into critical tactical advantages. Imagine a coastal castle with its vulnerable seaward side, suddenly protected by a receding tide that exposes vast stretches of treacherous mudflats, making a direct assault impossible. Or conversely, picture an attacking fleet waiting for the incoming tide to sweep their ships swiftly and silently towards a besieged city, catching defenders off guard. The strategic placement of obstacles, which we just discussed, also gained immense power when integrated with the understanding of currents. Engineers would deliberately position their submerged barriers, like chains or sharpened stakes, in areas where currents were strongest. This wasn't merely about causing damage, it was about amplifying the effect. A strong current could push an unsuspecting enemy ship directly onto a hidden spike field, or relentlessly drag a snared vessel against a submerged chain, increasing the likelihood of structural damage and making escape nearly impossible. This foresight turned the river's natural power into a destructive force multiplier, guiding enemy ships into predetermined killing zones without direct human intervention. It demonstrated a profound respect for the river's will, redirecting its energy for military gain. Exploiting tides and currents wasn't just about defense, it was also a critical component of offensive operations and logistical support. An invading army might time their river crossing to coincide with a period of slack tide, ensuring their pontoon bridges weren't swept away by strong currents, or allowing their barges to be ferried across with minimal effort. Conversely, a retreating force might use the outgoing tide to make a swift escape, outpacing pursuers who struggled against the flow. For navies operating in estuaries or coastal waters, predicting tidal movements was essential for navigation, ensuring their ships didn't run aground or get trapped in shallow waters. This meticulous attention to environmental detail was a testament to the sophistication of medieval military planning, where every natural element, from hidden rocks to the very movement of the sea, was meticulously factored into the grand strategy. It truly showed how natural flows were integrated into every aspect of military planning, revealing a landscape that was not just traversed but actively manipulated. Moving beyond the immediate defensive and logistical uses of water, we enter a realm that pushes the boundaries of medieval engineering thought, the theoretical application of water power to siege engines. While not as universally documented or widespread as moats or flood defenses, the very idea of harnessing a river's force to aid in an attack speaks volumes about the innovative spirit of the era's most advanced minds. Imagine for a moment a brilliant engineer standing beside a roaring river, not just seeing an obstacle or a defensive advantage, but envisioning a colossal machine driven by the very current of the water itself. Could water power have been used to turn a heavy winch, perhaps to wind up the enormous counterweight of a trebuchet, enabling faster reloading times or allowing for even heavier projectiles to be launched with less manual labor? Given the sheer effort involved in operating these massive war machines, any mechanical advantage would have been revolutionary. Picture a series of gears and levers driven by a powerful water wheel, slowly ratcheting back the arm of a giant stone thrower, unleashing devastation upon besieged walls with unprecedented speed and consistency. This would represent a significant leap from human and animal power, which dominated siege operations, offering a continuous, tireless source of energy. Or consider the possibility of large pumps driven by water wheels employed during a siege. While the primary use of pumps might seem defensive, like draining a flooded area or maintaining a moat, an offensive application could have involved specialized pumps for unique siege tactics. Perhaps pumping vast quantities of water to undermine foundations, or even to create impassable bogs on demand in front of a particularly stubborn section of wall. This isn't about traditional irrigation. It's about weaponizing controlled streams of water to achieve specific, destructive effects on a battlefield. While direct evidence for such complex, water-powered siege engines remains scarce, the underlying principles of water power were certainly understood. Watermills were already common, grinding grain and performing other tasks. It stands to reason that the most forward-thinking engineers, those who constantly sought new ways to solve military problems, would have pondered how this readily available, potent energy source could be adapted for the brutal demands of siege warfare. It's a testament to their continuous quest for innovation, forever seeking to bend the elements to their will, pushing the theoretical limits of what was achievable with their understanding of natural forces. But even as these brilliant minds dreamed of water-powered siege engines and innovative flood defenses, they wrestled with the harsh realities of their time. Medieval hydrological engineering, from the grandest canal to the simplest sluice gate, was a monumental undertaking, fraught with immense challenges that would daunt even modern engineers. Imagine trying to build a massive dam or divert an entire river with nothing more than shovels, picks, and rudimentary hand tools. There were no bulldozers, no concrete mixers, no digital surveying equipment to guide them. Every cubic foot of earth moved, every stone placed, every timber cut and fitted, was the result of back-breaking manual labor, often performed by hundreds or even thousands of workers. This reliance on human brawn meant projects progressed at a painstaking pace, requiring vast amounts of time and resources. Then there was the constant, unpredictable force of nature itself. Rivers swelled unexpectedly with seasonal rains, turning carefully dug channels into raging torrents and washing away weeks or even months of painstakingly erected structures. Frozen ground in winter made digging impossible, while scorching summers could dry up water sources, rendering defensive moats useless. Medieval engineers had to contend with the whims of weather patterns, often without the benefit of long-term meteorological data that we take for granted today. They relied on local knowledge, observation, and generations of accumulated wisdom to predict and adapt to these environmental variables. This constant battle against the elements meant that their designs had to be inherently robust, built to withstand not just enemy attacks, but also the relentless, often destructive power of the natural world. The materials available to them also presented significant limitations. While they had access to timber, stone, and earth, the quality and consistency of these materials could vary greatly. They lacked advanced cementing agents, relying on compacted earth, clay, and simple lime mortars that were far less durable than modern concrete. Constructing watertight structures, like prolonged aqueducts or complex sluice gates, required a profound understanding of material properties and an almost intuitive grasp of hydrodynamics. They couldn't simply order a specific type of steel or a high-strength composite. They had to make do with what was locally available, shaping it with skill and ingenuity to achieve their desired outcomes. This forced them to be incredibly inventive with basic resources, often developing techniques that were remarkably effective given the constraints, turning simple materials into sophisticated engineering solutions. Furthermore, the concept of standardized measurements and universally accepted engineering principles was still rudimentary. Knowledge was often passed down through apprenticeship from master to apprentice, relying on practical experience rather than theoretical models. There were no comprehensive textbooks on hydraulic engineering, no digital simulations to test designs before construction. Each project was, in many ways, an experiment, built on a foundation of trial and error and the accumulated wisdom of past failures and successes. The engineers themselves often learned on the job, honing their skills through direct engagement with the physical challenges of water management. This made every successful large-scale water project an even more remarkable achievement, a testament to their practical brilliance and their ability to innovate within severe technological and intellectual confines, pushing the boundaries of what was thought possible with the tools at hand. Given these monumental challenges, the role of accurate surveying and mapping became absolutely paramount for medieval engineers engaged in water warfare. You see, without the precise measurements and detailed understanding of the landscape provided by sophisticated modern tools, their ability to harness or manipulate water was entirely dependent on what they could visually observe and painstakingly record. They couldn't just sketch a rough idea. Every diversion channel, every defensive moat, every planned inundation required an intimate, almost intuitive, knowledge of the terrain's contours, elevations, and existing water flows. It was like trying to sculpt a complex, moving liquid artwork blindfolded if they didn't have a clear picture in their minds of how water would behave across different gradients and soil types. This meant early forms of mapping, though rudimentary by today's standards, were nothing short of vital. Imagine walking miles across uneven fields, carrying simple tools like ropes, measuring rods, and perhaps a basic level or plumb bob. Medieval surveyors would meticulously measure distances, estimate elevations, and note the courses of streams and rivers. These detailed reconnaissance missions were foundational. They allowed engineers to conceptualize where a dam could hold water, which areas would naturally flood with a diverted stream, or how deep a defensive ditch might need to be to remain effective year-round. These observations weren't just recorded as numbers, they often translated into functional, if not always perfectly to scale, sketch maps. These hand-drawn maps might show key landmarks, the paths of rivers, the locations of proposed fortifications, and crucially, the relative heights of different land features. They were blueprints for hydrological strategy, allowing military leaders and engineers to visualize the battlefield not just in terms of solid ground, but as a dynamic liquid environment. These simple maps and detailed surveys also served as critical planning tools. Before a siege, engineers would scout the surrounding area, identifying potential water sources for their own army, or, more nefariously, for disrupting the enemy's supply. They would pinpoint choke points in rivers for blockades, suitable locations for pontoon bridges, or areas where intentional flooding could create impassable barriers. The maps became indispensable for coordinating large-scale projects, allowing engineers to communicate their plans effectively to the laborers and soldiers who would execute them. They could point to specific areas on a map and say, "Here is where the new channel will begin," or "This is the low-lying field we intend to inundate." Without such foundational visual and measured data, these complex operations would have been impossible to orchestrate with any degree of accuracy or control. The ability to visualize and plan the movement of water across the land, even with such basic tools, was a profound strategic advantage, demonstrating a deep understanding of geography and hydrology that was far ahead of its time. These early cartographic efforts, born out of military necessity, laid foundational groundwork for more sophisticated mapping techniques that would evolve over centuries. So, who were these masterminds of water, these brilliant minds who could read the land like an open book and bend rivers to their will? They weren't your typical knights or feudal lords. The medieval engineer, particularly one skilled in hydrology, was a rare and invaluable individual, often operating at the intersection of practical skill, academic knowledge, and sheer ingenuity. Many of these unsung heroes came from unexpected backgrounds, and their training was a fascinating blend of inherited wisdom, meticulous observation, and hands-on experience. Often, you'd find these experts among the monastic orders. Monasteries, especially those of the Cistercians, were centers of innovation in agriculture and resource management. Monks needed reliable water supplies for their communities, for sanitation, for powering mills to grind grain, and even for fish ponds. Through generations of trial and error, observation, and the meticulous recording of data, they became masters of hydraulic engineering. They understood the principles of gravity, water flow, and how to build durable structures like dams, sluices, and aqueducts. Their practical knowledge, gained from managing water for peaceful purposes, translated directly into military applications when the need arose. They were the original civil engineers, and their understanding of water was unparalleled. Beyond the monasteries, master masons, the architects and builders of cathedrals and castles, also possessed crucial expertise. They understood structural integrity, the properties of different building materials, and how to lay foundations that could withstand the immense pressures of water. When a lord needed a formidable moat or a complex system of defensive waterways, it was often the master mason who oversaw the project. Their training was typically an apprenticeship, a long and rigorous process of learning from seasoned masters, starting with basic tasks and gradually progressing to more complex design. They learned by doing, by observing, and by solving real-world problems on massive construction sites. Then there were the more specialized individuals, perhaps not formal engineers in the modern sense, but experts in specific hydraulic works. These could be millwrights, deeply knowledgeable about the mechanics of water wheels and the diversion of streams, or even local farmers who, through generations of working the land, understood the nuances of irrigation and drainage in their particular region. Warfare often brought these disparate forms of knowledge together. A military commander might consult with a local peasant about the best place to divert a stream, then task a master mason with building the necessary structures, all coordinated by someone with a broader understanding of military strategy and hydrological principles. What truly set these medieval hydraulic engineers apart was their unique blend of theoretical understanding and hands-on skill. They didn't have calculus or advanced physics, but they possessed an intuitive grasp of how water behaved. They understood gradients, pressure, and the immense force of moving water. They could look at a landscape and envision where a channel could be dug, how a river could be dammed, or where a floodgate should be placed. This wasn't merely academic knowledge, it was knowledge forged in the mud and stone, gained from countless hours of observation, experimentation, and hard physical labor. They were problem solvers who learned directly from nature, adapting their designs to the specific challenges of each terrain. Their contributions were fundamental to medieval warfare, yet their names are largely lost to history, leaving behind only the enduring legacy of their remarkable, water-sculpted defenses. With that understanding of the medieval water engineer, let's now turn our attention to one of the most compelling examples of water warfare in action, the pivotal Siege of Rowan, which took place from 1418 to 1419. This wasn't just a conventional siege, it was a masterclass in hydrological strategy, showcasing how both attackers and defenders leveraged water to devastating effect. Rowan, a vital city in Normandy, sat strategically on the River Seine, making it a prime target for King Henry V of England during the 100 Years' War. Its location on the river was both its greatest asset and ultimately its most vulnerable point. The English under Henry V understood this perfectly. Their offensive strategy hinged on controlling the Seine. First, they imposed a strict naval blockade, deploying ships both upstream and downstream from Rowan. This wasn't just about preventing reinforcements or supplies from reaching the besieged city. It was about isolating Rowan entirely, cutting off its lifeline to the outside world. Imagine the frustration and despair growing within the city walls as no new food, no military aid, and no messages could pass through. The river, once a bustling artery of commerce and communication, became a chokehold applied by the English Navy. This blockade wasn't a sudden, dramatic assault, but a slow, suffocating squeeze designed to starve the city into submission. The English ships effectively transformed the mighty Seine into a weapon of deprivation, demonstrating that control over waterways could be as potent as any siege engine. But the English didn't stop there. They also worked to control access points along the river, setting up fortified camps and observation posts to ensure no one could slip through their watery net. This meticulous control over the Seine meant that Rowan's defenders were trapped, unable to receive external relief. Meanwhile, the French defenders within Rowan weren't passive. They too were masters of water manipulation, albeit in a defensive capacity. The city of Rowan had a complex internal water system, fed by various streams and springs, designed to provide fresh water to its citizens and to fill its defensive moats. As the siege wore on, the French engineers meticulously managed these internal resources. They ensured that the city's wells and conduits continued to function, providing at least some access to drinking water, a critical factor for survival during a prolonged siege. More importantly, they maintained and possibly even enhanced the water levels in Rowan's formidable moats. These moats, already a significant defensive barrier, became even more crucial under siege. They hindered English attempts to bring up siege towers and battering rams, forcing them to spend precious time and resources trying to bridge or drain the watery defenses. The deep, often muddy, and sometimes swift-flowing water made direct assaults extremely hazardous for the English soldiers. Any attempt to cross the moats became a slow, exposed, and dangerous endeavor, turning the very ground around the city into a treacherous obstacle course. This interplay between the English offensive use of the Seine for blockade and the French defensive use of their internal water systems for fortification created a fascinating hydrological chess match, where every drop of water, every flow, every strategic position along the river became a move in a deadly game of war. The Siege of Rowan stands as a stark reminder of how deeply medieval military strategists understood and utilized the power of water, making it an indispensable element of both offensive and defensive operations. While the Siege of Rowan gives us a clear window into medieval hydrological warfare, let's fast forward a bit in history for an even more dramatic illustration of water's power: the Siege of Leiden in 1574. Though technically beyond the strict medieval timeframe, this event perfectly encapsulates the ultimate potential of controlled flooding as an overwhelming defensive weapon, turning a desperate situation into a miraculous victory. The city of Leiden, in what is now the Netherlands, found itself under siege by Spanish forces during the 80 Years' War. The Spanish were determined to crush the Dutch revolt, and Leiden was a crucial stronghold. The citizens and garrison were pushed to the brink, facing starvation and relentless attacks, yet their resolve remained unshaken. What set Leiden apart was its precarious position in a low-lying region crisscrossed by canals and rivers, much of it below sea level and protected by dikes. This unique geography, usually a vulnerability, became their salvation. Prince William of Orange, leader of the Dutch rebels, conceived a daring and seemingly impossible plan: to break the dikes and flood the surrounding countryside, using the sea itself to drive off the besiegers. This wasn't a small-scale diversion. This was an act of environmental warfare on an unprecedented scale. The decision to inundate their own land was fraught with risk, causing immense hardship for the local population whose farms and villages would be submerged, but it was seen as the only viable path to freedom. The execution of this plan was a monumental feat of hydraulic engineering combined with sheer human will. Dutch engineers, working against time and under constant threat from the Spanish, systematically breached dikes in multiple locations. They started by cutting the main dike that separated the land from the ocean, allowing the North Sea's waters to flow inland. This was a slow process, as the initial breaches only allowed a trickle. To accelerate the flooding, they then opened sluice gates and cut smaller dikes further inland, guiding the water through a network of canals and low-lying fields towards Leiden. It was a race against time as the Spanish watched with a mixture of disbelief and growing alarm. The result was a transformed landscape. What had once been fields and roads became a vast, shallow inland sea stretching for miles. This was not deep enough for large ships, but it was too deep for the Spanish soldiers to wade through or march across. Their siege lines, carefully constructed and manned, suddenly found themselves surrounded by water, their encampments turned into isolated islands. Supplies dwindled, disease spread, and morale plummeted among the Spanish troops, who were simply not equipped for aquatic warfare. Meanwhile, the Dutch, utilizing a small fleet of shallow draft flat-bottomed boats, known as flyboats, were able to navigate these newly formed waterways. These boats carried vital provisions to the starving city and launched harassing attacks against the stranded Spanish positions. The climax came when a powerful storm surge, perhaps a final act of divine intervention in the eyes of the besieged Dutch, pushed even more water inland, making the Spanish position utterly untenable. Confronted by the rising waters, an impending Dutch naval assault across the flooded plains, and their own desperate conditions, the Spanish forces were forced to retreat in disarray, abandoning their siege engines and supplies. The relief of Leiden was one of the most celebrated victories of the Dutch revolt, a testament to how intelligent and audacious hydrological warfare could turn the tide of a conflict. It demonstrated that water, when harnessed effectively, wasn't just a defensive barrier but could become an active, dynamic force capable of routing an entire army, reshaping the battlefield itself in a truly spectacular fashion. The dramatic events at Leiden clearly highlight how deeply water warfare intertwined with logistical planning in medieval and early modern conflicts. It wasn't just about constructing defenses or launching attacks. Commanders had to grapple with how water influenced every aspect of moving and supplying an army. Perhaps the most fundamental concern for any force on the march was access to potable water for their own consumption. Armies, whether attacking or defending, comprised thousands of soldiers and often many more non-combatants and horses, all requiring vast quantities of water daily. A reliable, uncontaminated water source could mean the difference between a healthy, effective fighting force and one crippled by disease and dehydration. Commanders constantly scouted ahead, assessing river crossings, wells, and spring locations, understanding that a seemingly minor detail like a polluted stream could wreak havoc on their plans. Beyond direct consumption, the navigability of rivers and other waterways became a paramount consideration for transporting supplies. Land transport in the medieval era was notoriously slow, expensive, and vulnerable, relying on often poor roads or muddy tracks. A single barge on a river could carry many times the load of a dozen ox carts, and do so far more efficiently. This made rivers vital arteries for moving everything from provisions and grain to siege engines and reinforcements. Armies often advanced along riverbanks, using the waterway as their primary supply line, or established forward operating bases at key river junctions. Disrupting these riverine supply routes, whether through blockades, submerged obstacles, or even changing water levels, became a potent form of economic warfare, starving out garrisons or forcing armies to abandon their positions. Then there was the constant, ever-present threat of enemy water manipulation. Commanders couldn't just assume a river would stay put or that a well would remain uncontaminated. As we've seen, the intentional flooding of areas or the diversion of water sources could entirely reshape the battlefield, turning what seemed like a clear path into an impassable swamp. This meant that military engineers and strategists had to add hydrological intelligence to their reconnaissance checklist. They needed to understand the local topography, the network of dikes and canals, and the locations of sluice gates, not just to employ these tactics themselves, but to anticipate and counter their enemies' use of them. A seemingly minor consideration, like the state of a local dam upstream, could suddenly become a major strategic point, dictating troop movements or even the entire outcome of a campaign. The siege of a city or a fortress further amplified these logistical challenges. Besieging armies needed to ensure their own water supply while simultaneously trying to cut off the defenders. This often involved digging trenches to divert streams, poisoning wells, or bombarding aqueducts. For the besieged, every drop of water suddenly became precious, and reliance on internal wells or rainwater collection systems was critical. The vulnerability of a city's water infrastructure often became its Achilles heel, making water control a decisive factor in prolonged sieges. In essence, water transformed from a natural resource into a complex variable in the military equation, demanding constant vigilance and ingenious solutions from those who commanded armies. Beyond its physical impact, the manipulation of water became a potent tool in the psychological arsenal of medieval warfare. Imagine the sheer terror of a defending garrison as their only well ran dry, or the chilling realization that their precious cisterns were being systematically poisoned. Cutting off a city's water supply was one of the most effective ways to induce panic and despair without directly engaging in costly open combat. The knowledge that thirst was slowly but surely closing in often eroded morale faster than any bombardment. Defenders would gaze from their battlements, watching their precious reserves dwindle, knowing that every day brought them closer to an agonizing choice: surrender or perish. This psychological pressure could turn even the most stalwart defenders into a desperate, broken force, making them vulnerable to demands they would otherwise never consider. It wasn't just about the physical discomfort, it was about the utter loss of control, the gnawing fear that life itself was being slowly choked away. Conversely, for an attacking force, the sight of vast, deliberately flooded plains stretching for miles could be utterly demoralizing. Picture an army, confident in its advance, suddenly confronted by an endless, muddy expanse where roads vanished and solid ground became treacherous marshland. This wasn't just an inconvenience, it signaled the futility of their efforts, the realization that nature itself, manipulated by their ingenious enemy, was conspiring against them. The endless slogging through waterlogged fields, the constant fear of hidden ditches or submerged obstacles, and the sheer physical exhaustion of such an advance could break an army's spirit long before they reached the walls of a city. Their horses would struggle, their heavy siege equipment would become bogged down, and the promise of a swift victory would evaporate into a frustrating, seemingly insurmountable quagmire. This visible, tangible barrier stretching to the horizon served as a constant psychological blow, reminding them that every step was a battle against the very landscape, a battle they might not win. The psychological impact extended to the civilian population as well. For those trapped within besieged walls, the sight of their fields submerged or their vital river altered was a powerful symbol of their vulnerability and the enemy's complete control. It drove home the terrifying reality that their lives, their livelihoods, and their very existence were at the mercy of their attackers. The lack of clean drinking water led to disease, not just physically weakening the populace, but also spreading fear and hopelessness as they witnessed their loved ones succumb to illnesses brought on by contaminated conditions. The constant worry about where the next drop of water would come from, coupled with the stench of stagnant pools and the fear of unseen dangers, created an atmosphere of pervasive anxiety. These invisible yet deeply felt pressures were often more effective than direct military assaults in forcing a surrender, demonstrating that fear, expertly wielded through the control of water, could be just as potent and destructive as any physical weapon. From the earliest days of human settlement, the strategic value of water was clear, but medieval engineers pushed this understanding to astonishing new heights, transforming simple defensive features into intricate, powerful systems. Initially, a basic moat surrounding a castle or town was the primary water-based defense. These early moats were often little more than dug ditches, sometimes fed by natural streams or rainfall, designed to impede direct assault and make scaling walls more difficult. Their primary purpose was creating a physical barrier, forcing attackers to bridge or fill them under fire, exposing themselves to the defenders. But the medieval mind, constantly seeking an edge in an age of brutal conflict, soon saw far greater potential. The true evolution began with the introduction of sophisticated sluice gates and dams. This wasn't just about digging a ditch and letting it fill. It was about active water management. Engineers learned to control water levels with remarkable precision. Sluice gates, often robust wooden or iron mechanisms, allowed defenders to rapidly flood an area, turning dry land into a deep, impassable lake almost instantaneously, or conversely, to drain a flooded area if needed for counterattacks or maintenance. Dams built upstream or strategically placed within waterways could create large reservoirs, ensuring a constant supply of water for the moats and potentially for overwhelming floods if the situation demanded it. This meant the defense was no longer static. It could be dynamic, responsive to the immediate threat. Imagine a besieging army confidently advancing, only to find their path suddenly submerged by a controlled release of water, turning their carefully planned approach into a chaotic struggle against the elements. This dynamic control led to the development of interconnected waterway systems. Instead of just a single moat, some advanced fortifications featured multiple concentric rings of water defenses, each with its own set of sluice gates, creating layers of watery obstacles. These systems could also be integrated with natural topography, guiding water through various channels around curtain walls and even into underground passages. This allowed for an incredible degree of flexibility. Defenders could choose to flood certain sections while keeping others dry, creating traps for advancing forces or simply guiding the enemy into predetermined killing zones. The defensive blueprint became a complex hydraulic puzzle where every stream, pond, and ditch played a part in the overall strategy. The engineers of this era understood that water could be a fluid, ever-changing shield, far more versatile than static stone walls alone. Furthermore, water became an integral part of the very design of defensive architecture. Towers and gatehouses were often positioned to overlook and control sluice mechanisms, making their operation a core part of the fortress's defense. The thickness and depth of moats were carefully calculated based on the surrounding terrain and available water sources, optimizing their defensive capabilities against specific types of siege equipment. The sheer scale of some of these projects was monumental. Entire landscapes were reshaped, rivers diverted, and vast areas excavated to maximize water's defensive potential. These were not just castles with water around them, they were water castles where the liquid element was as fundamental to their strength as stone and timber. This continuous quest to optimize water's strategic advantage truly highlights the ingenuity and foresight of medieval engineers, forever changing the face of fortification and battlefield strategy. Beyond its role in defense and attack, water played another, often overlooked but critically important role during medieval sieges: sanitation and disease. While not a weapon in the traditional sense, a contaminated water supply could prove far more deadly than any siege engine or direct assault. For both the besieged and the besiegers, access to clean water was literally a matter of life or death, making water a complex dual-edged sword, a life-giver that could rapidly turn into a silent killer. Within the cramped, unsanitary conditions of a besieged castle or town, maintaining a potable water source was a constant, desperate struggle. Wells could be poisoned, cisterns tainted, and rivers downstream from large encampments often became conduits of disease. A single contaminated well could quickly spread dysentery, typhoid, or other waterborne illnesses through an entire garrison, decimating its fighting strength without a single arrow being fired. This made protecting internal water sources a paramount defensive objective, sometimes even more critical than defending the walls themselves. Conversely, besieging armies faced similar, if not greater, challenges. Large concentrations of soldiers, camp followers, and animals, often without adequate latrine facilities or knowledge of basic hygiene, would inevitably pollute nearby streams and rivers, their primary water sources. Epidemics could sweep through a besieging force, turning a well-organized army into a chaotic hospital camp. Historical accounts are rife with examples of sieges abandoned not because of valiant defense, but because disease had rendered the attackers incapable of continuing. This hidden battle, fought against invisible microbes, often determined the fate of sieges more decisively than any direct combat, making clean water a strategic asset for both sides. The stark reality was that the very resource essential for survival also presented the greatest threat to health. Medieval engineers and military leaders understood this paradox, even if their understanding of germ theory was non-existent. They knew empirically that stagnant water, human waste, and unburied corpses led to sickness. This knowledge informed some of their design choices, such as positioning latrines to flush into rivers downstream from the main water intake points, or digging separate wells for drinking water and other uses. Yet, their efforts were often insufficient, especially during extended sieges where resources dwindled and hygiene deteriorated. The psychological impact of disease was also profound. The constant threat of illness, the sight of comrades falling ill and dying from unseen enemies, could break morale faster than any enemy attack. Water, therefore, became a silent partner in psychological warfare, its purity determining not just physical survival, but also the mental fortitude of those enduring the siege. This continuous struggle to manage water, both for sustenance and to ward off disease, highlights a critical, often tragic, aspect of medieval warfare that unfolded quietly within the walls and among the encampments, a testament to water's enduring importance in every facet of human conflict. Given water's incredible power, both as a tool for defense and attack, and as we just explored, a silent killer through disease, it begs the question, did medieval societies have any codes or customs regarding its weaponization? Or was it simply a free-for-all where anything went in the brutal pursuit of victory? The truth is, the concept of ethical warfare, as we understand it today, was largely non-existent in the medieval period, particularly when it came to tactics of siege. When a city or castle refused to surrender, the attacking force often felt justified in employing any means necessary to achieve their objective, and that often included targeting the very resources essential for life. Poisoning water supplies, for instance, was a particularly grim tactic. While there are historical accounts of its use, it wasn't universally embraced, perhaps less out of ethical qualms and more due to practical concerns. It was incredibly difficult to effectively poison a large-scale water source without also risking harm to one's own troops or the civilian population upon occupation. Moreover, the psychological impact of such an act could be immense, potentially hardening the resolve of defenders rather than breaking it. Yet, the devastation caused by poisoned wells or tainted rivers was undeniable, making it a terrifying prospect for any besieged community. The lack of scientific understanding about germs meant that while medieval people recognized the link between contaminated water and disease, they attributed it to bad humors or divine displeasure rather than microbes. This made the act of poisoning feel even more sinister, tapping into primal fears about unseen threats. Beyond outright poisoning, the diversion of water supplies was a far more common and accepted tactic. Cutting off a city's access to fresh water was a highly effective way to force surrender without incurring the heavy casualties of a direct assault. Rivers could be dammed, canals rerouted, and aqueducts destroyed. These actions, while devastating to the civilian population, were generally viewed as legitimate acts of war, falling under the umbrella of siege warfare. After all, if you could starve a city into submission by cutting off food supplies, why not dehydrate it by cutting off water? The suffering inflicted was immense, but it was seen as a necessary evil to achieve a strategic goal. There was little in the way of international law or widespread treaties to govern such actions. Warfare was largely dictated by local customs, the power dynamics between factions, and the perceived legitimacy of the conflict. Religious doctrines, while often shaping the overall morality of warfare, rarely delved into the specifics of hydraulic tactics. Knights, bound by codes of chivalry, were expected to show mercy to their captured enemies and protect the innocent, but these codes often blurred when it came to the harsh realities of siege. The suffering of civilians, while regrettable, was often seen as an unavoidable consequence of a prolonged siege. The focus was on achieving victory, and if manipulating water could hasten that outcome, it was a tool to be used. This pragmatic approach underscores the brutal effectiveness of water as a weapon in an era where survival and conquest superseded many other considerations. It shows us that while engineers were pushing the boundaries of what was possible, the ethical frameworks to guide such power were still very much in their infancy. Despite their remarkable ingenuity in weaponizing water, medieval engineers operated within significant technological constraints, which makes their achievements all the more impressive. They lacked many of the scientific understandings we take for granted today, like precise fluid dynamics or advanced surveying equipment. Imagine trying to calculate the optimal slope for a canal or the water pressure needed to breach a dam, armed only with basic levels, plumb bobs, and a deep understanding of practical experience passed down through generations. There were no mechanical diggers, no specialized pumps beyond the most rudimentary designs, and definitely no heavy machinery to assist in moving the colossal amounts of earth and stone required for large-scale hydrological projects. All this work was done by hand with picks, shovels, and simple levers, relying on the sheer muscle power of hundreds, sometimes thousands, of laborers. The materials were also limited: stone, timber, packed earth, and rudimentary mortars. Building a durable dam or a complex sluice system required an intuitive grasp of geology and material science that was honed through trial and error, often over centuries. Yet, within these limitations, medieval engineers achieved significant breakthroughs in hydraulic engineering. One key innovation was the widespread adoption and refinement of the sluice gate. While simple in concept, a movable barrier controlling water flow, its sophisticated application was crucial for medieval water management. Early sluices were basic wooden planks, but over time they evolved into complex, often iron-reinforced, systems operated by winches and gearing. These allowed for precise control over water levels in moats, the direction of flow for diversions, and the rapid discharge of water for controlled flooding. The ability to precisely manage water flow meant engineers could now effectively fill and drain moats at will, or inundate vast areas of land within a matter of hours, turning a natural landscape into an impenetrable watery defense. This precision was a game-changer, moving beyond mere damming to active, dynamic water control. Another area of innovation was the development of more efficient water-lifting devices. While not always directly weaponized, these technologies were foundational to many hydrological warfare tactics. Beyond the simple bucket and rope, engineers learned to adapt existing technologies like the Archimedean screw or the Persian wheel, often powered by animals or even the current of the river itself, to move water uphill or over long distances. Such advancements were essential for maintaining water levels in moats that weren't fed by natural springs, or for supplying besieged garrisons with fresh water from distant sources. The Roman aqueduct system, once thought lost to the Dark Ages, saw a partial resurgence in various forms, as medieval communities and fortifications found ways to bring water reliably into their strongholds, ensuring self-sufficiency and prolonging resistance against sieges. Their methods might seem basic by today's standards, but they were pioneering for their time, revealing a deep mechanical understanding and a relentless drive to overcome environmental challenges. The integration of water systems into fortifications also represents a significant leap. It wasn't just about digging a ditch and filling it with water. It was about creating interconnected networks of moats, canals, and drains that could be managed to optimize defense. Castle designers learned to incorporate water features directly into the architectural plan, building walls that rose directly from the water's edge, or designing hidden culverts that could be opened to flood approach trenches. This holistic approach transformed the battlefield into an extension of the fortress itself. These complex systems required immense foresight and planning, often spanning years to construct, reflecting a long-term strategic vision that went far beyond immediate military needs. These engineering feats stand as a testament to the fact that even with limited tools, medieval minds could achieve truly remarkable things. shaping their world and securing their survival through a profound mastery of the natural elements. While medieval engineers pushed the boundaries of what was possible with water, the relentless march of military technology eventually began to challenge the supremacy of these hydrological defenses. The arrival of gunpowder and, more critically, advanced siege artillery in the late medieval and early modern periods shifted the balance of power. Massive stone walls, once thought impregnable when protected by even the widest and deepest moats, suddenly faced a formidable new threat. Cannons could lob heavy projectiles with increasing accuracy and destructive power, eventually capable of breaching even the thickest fortifications. A direct hit from a large bombard could collapse sections of a wall, creating a breach that water defenses alone could not always conceal or protect. The speed and mobility of these new weapons also reduced the time available for defenders to execute complex water-based operations like controlled flooding, which often took days or weeks to fully implement. The very static nature of many elaborate water defenses became a liability when confronted with dynamic, explosive force. However, it would be a mistake to think that water warfare simply vanished. Instead, its role evolved and adapted to these new realities. Moats, while less effective against direct cannon fire, still served several crucial purposes. They forced attackers to build elaborate causeways or employ specialized pontoons, slowing down their approach and making them vulnerable targets. This delay tactic was invaluable, especially in an era when siege campaigns were often races against time, limited by supplies and the onset of winter. Furthermore, the psychological impact of a water barrier remained potent. The sheer effort required to cross a well-maintained moat, often under enemy fire, continued to wear down besiegers and demoralize their troops. Military engineers began to design new fortifications known as Trace Italian or star forts, which incorporated wider, deeper moats often integrated with earthen ramparts designed to absorb cannon fire. These new fortifications maximized the defensive potential of water by making it an integral part of a multi-layered defense system rather than the sole protective element. Beyond static defenses, the principles of hydrological warfare continued to manifest in other ways. Diversion and deprivation tactics, for example, remained highly effective regardless of advancements in gunpowder. Cutting off a besieged city's water supply or flooding its agricultural lands could still force a surrender without firing a single shot, leveraging thirst and famine as potent, silent weapons. The ability to control waterways for transport and communication also retained its strategic importance. Rivers continued to be vital arteries for moving troops, supplies, and artillery, making riverine control and naval blockades enduring aspects of warfare well into the modern era. The principles of exploiting currents, creating hidden obstacles, and managing strategic waterways remained relevant, transforming from medieval ingenuity to modern military doctrine. Even the Dutch, much later, would perfect the art of inundation in their struggles for independence, demonstrating that large-scale controlled flooding could still be a decisive defensive measure against technologically superior forces. Therefore, rather than a simple decline, it was more a transformation. The era of water as the primary, unyielding defensive barrier came to an end with the rise of widespread gunpowder weaponry. Yet, the underlying strategic principles and tactical applications of water manipulation persisted. Engineers continued to integrate water into defensive designs, albeit in new forms, and commanders still recognized the immense logistical and psychological power of controlling hydrological resources. The basic lessons learned from medieval water warfare, the importance of controlling flow, creating barriers and disrupting enemy access became foundational elements that would subtly resurface and adapt in military strategies for centuries to come, proving that the weaponization of natural elements endures beyond specific technologies. The fundamental principles of how water shaped conflicts in the medieval era still echo powerfully in modern military strategy, though perhaps in forms unrecognizable to an old-world engineer. Today, military planners and strategists consider hydrological assets, vast reservoirs, complex dam systems, and intricate networks of waterways with the same strategic intensity that medieval commanders applied to their moats and river blockades. It is not about breaching a castle wall with cannon fire anymore. It is about controlling the flow of vital resources, disrupting supply lines, and creating defensive barriers on a scale our ancestors could only dream of. Consider the strategic importance of dams, for example. These modern marvels of engineering designed to generate power, control floods, or provide irrigation instantly become critical tactical objectives in any large-scale conflict. Their destruction can cripple an enemy's infrastructure, plunging regions into darkness, inundating vast areas, or cutting off essential water supplies. Conversely, their protection becomes paramount, turning them into formidable defensive strongholds. Think of the intense scrutiny and military planning that goes into protecting major dams like the Hoover Dam or the Three Gorges Dam in any hypothetical scenario. Their very existence transforms them into strategic assets far beyond their intended civilian purposes, directly paralleling the medieval understanding of a watermill's dual military value. Moreover, waterways themselves, whether natural rivers or man-made canals, remain indispensable avenues for logistics and projection of power. Just as medieval riverine patrols guarded against enemy incursions and ensured the safe passage of goods, modern navies and specialized riverine forces maintain control over strategic rivers and coastal areas. The ability to move troops and heavy equipment along a river can be far more efficient than overland travel, especially in challenging terrain. This makes choke points along these waterways, such as bridges or narrow passages, critical targets for both defense and attack. The tactics for naval blockades, once executed with simple barges and longboats, now involve sophisticated vessels and submarines, but the underlying objective, to interdict supplies and isolate an enemy, remains remarkably consistent with the objectives of historical water-based blockades. Even the concept of controlled flooding, a hallmark of medieval and early modern defensive strategies, finds modern applications. While not as common in direct battlefield scenarios due to the scale of modern warfare, the strategic inundation of land to impede an advancing enemy or protect a vital area is still a viable, albeit extreme, option in certain contexts. The very thought process using the landscape itself, modified by water as a defensive weapon, is a direct descendant of medieval military thought. The enduring relevance of these ancient lessons underscores a timeless truth in warfare: the ability to understand, control, and manipulate the natural environment provides a unique and often decisive advantage. The battle for hydrological control might look different today, with satellites mapping water sources and advanced algorithms predicting flood patterns. But the core strategic principles are a testament to the ingenuity of those medieval engineers who first turned rivers into formidable weapons. Beyond the immediate strategic gains, the large-scale manipulation of rivers and landscapes for warfare in the medieval period often left behind profound and unintended environmental consequences. These weren't just temporary disturbances, they were significant alterations to ecosystems that could persist for decades, centuries, or even longer, subtly reshaping the natural world in ways that are still evident today. Think of a river diverted to fill a moat or to flood an entire valley for defensive purposes. While tactically brilliant, this act fundamentally changed the river's course, its flow rate, and its natural sediment transport. Fish populations would have been impacted, riparian habitats destroyed, and the delicate balance of the aquatic ecosystem thrown into disarray. The very act of weaponizing a natural feature fundamentally altered its environmental role. When engineers intentionally flooded vast tracts of land, as was done in the Low Countries, it created new wetlands. While some might see this as a beneficial environmental outcome in certain modern contexts, in the medieval period, these were often agricultural lands or areas of natural forest and meadow. The prolonged inundation would have killed existing vegetation, displaced or eliminated local wildlife, and drastically changed soil composition. Over time, these areas could become permanent marshes or bogs, transforming productive land into impassable terrain. The introduction of large bodies of standing water also changed local microclimates, potentially increasing humidity and fostering different species of insects and plants, sometimes with unforeseen negative effects on human health, like the spread of waterborne diseases. Consider, too, the long-term effects of damming and sluice gate construction, even for defensive purposes. These structures, built to control water levels for moats or to enable controlled flooding, disrupted the natural migration patterns of fish and other aquatic life. A river that was once a vibrant corridor for different species became segmented, leading to isolated populations and, in some cases, local extinctions. The siltation patterns also changed. Upstream from a dam, sediment would accumulate, potentially filling in sections of the riverbed, while downstream, the river might become clearer but also more erosive, digging deeper into its banks due to the lack of sediment. This wasn't merely a strategic inconvenience but a foundational shift in the river's geomorphology, a silent environmental scar left by human conflict. Even localized actions like digging extensive ditch systems or creating artificial ponds for water storage contributed to this environmental reshaping. These actions required massive earth movements, disrupting soil layers and changing drainage patterns across wide areas. The cumulative effect of countless such projects across a fragmented landscape meant that human conflict, driven by military necessity, inadvertently became a powerful agent of environmental change. The medieval world, often seen as less impactful on the environment than the Industrial Age, nevertheless bears the subtle, enduring marks of its engineers' efforts to turn water into weapons, a testament to how profoundly interwoven human endeavor and the natural world have always been. Of course, water was not just a tool for direct defense or attack. It also played a critical role in the art of military deception and camouflage. Medieval engineers understood that manipulating water could create illusions, hide critical assets, or obscure troop movements, adding an often overlooked layer to their strategic arsenal. Imagine a fortress that appeared to be surrounded by an impossibly wide and deep moat one day, only for that water level to subtly drop overnight, revealing hidden causeways or submerged obstacles that an enemy would then blunder into. This kind of dynamic deception was a testament to the engineers' mastery of hydrodynamics and their understanding of human psychology in warfare. One of the most effective ways water was used for tactical deception involved the creation of controlled flooded areas. While we've already discussed how these could bog down advancing armies, they could also serve as excellent cover for troop movements. An enemy might assume a flooded plain was impassable, only for a small force to navigate it by boat or through shallow, pre-scouted channels, silently flanking their position. The sheer scale and apparent uniformity of a vast flooded landscape could make it incredibly difficult for an enemy scout to discern hidden pathways, camouflaged boats, or even submerged defensive barriers. The water's reflective surface could further disorient observers, especially at dawn or dusk, blurring the lines between solid ground and deceptive depths. Changes in water levels around fortifications were another subtle yet powerful form of deception. Sluice gates could be opened or closed to either raise or lower the water in moats and surrounding wetlands. A sudden rise in water level might submerge previously visible bridge supports or reinforce the appearance of an impenetrable barrier, deterring an immediate assault. Conversely, a carefully orchestrated drop in water could hide defensive structures like sharpened stakes, caltrops, or even entire submerged ditches, only revealing them to an enemy when it was too late. These hidden obstacles would prove devastating to an unsuspecting attacking force, often causing panic and disarray as soldiers found themselves trapped or impaled in what appeared to be clear ground. Consider, too, the use of water to mask the true strength or weakness of a position. A wide, tranquil river might seem to offer easy passage for an enemy, leading them to underestimate the defensive preparations on the opposite bank. Underwater chains or hidden boom barriers, perhaps anchored to concealed pilings, could be raised at a critical moment to trap enemy vessels, turning a seemingly open waterway into a deadly ambush zone. Similarly, a seemingly impenetrable swamp, made so by controlled flooding, might secretly contain well-maintained, hidden paths known only to the defenders, allowing them to launch surprise raids or resupply their garrisons unseen. These subtle manipulations transformed natural features into active participants in the game of strategic concealment. The very act of controlling water also allowed medieval engineers to control visibility and access, creating a psychological advantage. Fog, often exacerbated by large bodies of water, could be exploited to conceal movements. Diversion trenches, far from a fortress, could draw enemy attention and resources to a false threat, while the real offensive preparations took place under the cover of a seemingly natural water feature. This ability to manipulate the environment for military advantage demonstrates a sophisticated understanding of both engineering and human perception, showing that medieval strategists were far more than just blunt force commanders. They were masters of illusion, using the very fluidity of water to their strategic advantage, adding a dynamic and unpredictable element to their art of warfare. Of course, all this ingenious manipulation of water, from defensive moats to large-scale flooding and intricate deception, came at a significant cost. The economics of water warfare were staggering, demanding immense resources, planning, and sustained investment. Medieval rulers and lords didn't just decide to build a moat, they committed to an undertaking that could drain treasuries and require years of effort. Consider first the sheer labor involved. Digging a wide, deep moat around a castle wasn't a task for a handful of men. It required hundreds, sometimes thousands, of laborers working for months or even years, often using only basic picks, shovels, and wheelbarrows. These were not specialized military engineers, but typically local peasants pressed into service or paid laborers who needed to be fed, housed, and supervised. Imagine the logistical nightmare of providing food and shelter for such a large workforce for an extended period, especially in remote areas. Then there was the specialized labor, the master masons and engineers who designed the systems, understood the flow of water, and oversaw the intricate construction of sluice gates, dams, and channels. Their expertise commanded high wages, adding another layer to the financial burden. Beyond labor, the materials themselves represented a substantial investment. While earth and stone were often locally sourced, transporting them, especially large quantities of rock for lining channels or building sturdy dams, required expensive animal power and carts. For structures that needed to withstand pressure and time, timber for palisades, iron for gate mechanisms, and even specialized tools for digging and shaping the landscape all had to be acquired. In an era where resources were often scarce and transportation difficult, securing these materials for large-scale water projects was a feat in itself, often necessitating long-distance trade or the diversion of resources from other crucial areas, like agriculture or other construction. The economic toll extended far beyond the initial construction. Maintaining these sophisticated water defenses was an ongoing expense. Moats needed regular dredging to prevent silting, sluice gates required repair, and channels had to be cleared of debris. Negligence could quickly render a formidable water defense useless, meaning continuous investment was necessary. Furthermore, the economic impact on the surrounding population could be immense. If agricultural land was intentionally flooded for defensive purposes, valuable crops were destroyed, leading to food shortages and economic hardship for the local populace. This wasn't merely a strategic decision. It was a devastating economic blow to the very people a lord was sworn to protect, highlighting the desperate measures sometimes taken in warfare. Conversely, launching hydrological attacks, such as diverting a river away from an enemy city or flooding their fields, also had significant economic implications for the aggressor. While the direct cost might seem lower than building a massive defensive system, the long-term consequences could be substantial. Such actions often led to prolonged sieges, which were incredibly expensive to maintain, requiring constant provisioning for the besieging army. Furthermore, destroying an enemy's water supply or agricultural base could cripple the very land an attacker hoped to eventually conquer, diminishing its value and creating a long-term economic liability rather than an asset. The financial burden wasn't just about what you spent, but also about what you destroyed, impacting future prospects. Ultimately, the decision to engage in water warfare wasn't taken lightly. It was a strategic choice with profound economic consequences, reflecting the immense value placed on defense and the desperate lengths to which medieval powers would go to secure their strongholds. The financial investment in turning rivers into weapons underscores the critical importance of these liquid defenses and the deep understanding that medieval leaders had of the interplay between engineering, resources, and military power. It was a costly endeavor, but one they clearly believed was worth every penny for the strategic advantage it provided. With the staggering economic realities of water warfare laid bare, it begs the question, how did those who lived through these ingenious and often devastating tactics perceive them? What did the chroniclers, the scribes, the ordinary people, and the besieged soldiers write about the strategic manipulation of rivers and the controlled flooding of landscapes? Stepping back in time, we find a rich tapestry of first-hand accounts and interpretations woven into medieval chronicles, letters, and various primary sources, offering us a glimpse into the human experience of these watery battles. These aren't just dry technical descriptions, they are often infused with awe, terror, and sometimes grudging admiration for the sheer scale of the engineering. For instance, chroniclers often detailed the construction of moats and the diversion of rivers with a mix of practical observation and a touch of the miraculous. They marveled at the transformation of the landscape, describing how a dry plain could become an impassable lake, or how a once-flowing river could be rerouted entirely. These accounts sometimes framed the success of such projects as divine favor, a testament to the righteousness of the cause, especially when a defensive flood turned back an enemy army. Imagine a chronicler from a besieged town writing about the rising waters that suddenly encircled their walls, not just as a military tactic, but as a providential intervention, saving them from imminent destruction. Their narratives reflect a society deeply connected to the land and its features, where altering a river's course was seen as an act of immense power, almost challenging the natural order. On the flip side, the human cost, especially for those experiencing hydrological attacks, comes through poignantly in many records. When a city's water supply was cut off or surrounding agricultural lands were deliberately flooded, the suffering was immense. Letters from besieged garrisons might speak of the ever-dwindling water reserves, the gnawing thirst, and the despair that set in as the enemy's hydraulic siege tightened its grip. These personal accounts, though rare and often filtered through the perspectives of literate elites, nevertheless paint a vivid picture of hardship. They might complain of the stench of stagnant water after a flood, the spread of disease, or the ruin of crops that supported their very existence. The psychological impact of watching your lifeline literally drain away or seeing your livelihood submerged was a powerful weapon, and the chroniclers captured this sense of desperation. Consider the accounts of the great sieges like that of Rowan, where French defenders and English attackers both manipulated the Seine and the city's internal water systems. Chroniclers from both sides would have diligently recorded the strategic importance of controlling the river, the efforts to build temporary bridges or blockages, and the constant vigilance required to prevent the enemy from gaining an advantage on the water. These historical records would often describe the ships and barges patrolling the river, the skirmishes on the water, and the overall strategic chess match played out on the liquid highway. Their focus was not just on land battles, but on the crucial role of the river in dictating logistics and preventing relief efforts. Moreover, we find interpretations that highlight the ingenuity and sometimes the moral ambiguity of water warfare. Was it considered legitimate to poison wells or divert water from civilian populations? While explicit ethical treatises on hydrological warfare are rare, chroniclers often express disdain or horror at tactics that caused widespread civilian suffering, even if deemed militarily effective. Accounts of scorched earth tactics that involved destroying fertile lands through flooding, particularly when carried out by an invading force, often carried a tone of condemnation, reflecting a societal understanding that such destruction went beyond the immediate military objective and inflicted long-lasting harm. They acknowledged the effectiveness of these methods but also highlighted their devastating consequences for non-combatants, revealing the early glimmers of a moral debate about the limits of warfare. Ultimately, these first-hand accounts and chronicler interpretations offer invaluable insights beyond engineering diagrams. They provide the human dimension of medieval water warfare, showing us how rivers and water bodies were not just obstacles or resources, but extensions of human will and ingenuity, shaping both the landscape and the lives within it. They remind us that behind every strategic decision and massive undertaking, there were people experiencing its profound and often brutal effects, leaving behind a written legacy of awe, fear, and resilience in the face of these watery weapons. Uncovering the secrets of medieval water warfare isn't just about poring over ancient texts. It's a dynamic field where modern science breathes new life into historical landscapes. Today, archaeologists and historians are leveraging incredible advancements in remote sensing and hydrological modeling to reconstruct these ingenious, often hidden, water warfare systems. Imagine using technology developed for mapping distant planets to understand how a medieval army diverted a river, or how a sophisticated network of moats and sluice gates once protected a fortress. This isn't science fiction, it's the cutting edge of historical research, bridging the divide between our digital present and the analog past. One of the most powerful tools in this modern toolkit is remote sensing. This involves gathering information about an area without making physical contact, often from aircraft or satellites. Techniques like LiDAR, which stands for light detection and ranging, can penetrate dense vegetation and modern surface features to reveal subtle changes in elevation, sometimes unveiling the buried remnants of ancient earthworks. Old riverbeds, diversion channels, and even the faint outlines of long-gone dams often leave a telltale signature in the topography that LiDAR can detect. Imagine an archaeologist flying a drone equipped with LiDAR over a seemingly flat field, and suddenly seeing the ghost of a medieval canal system appear on their screen, a waterway that hasn't seen water in 500 years. This allows researchers to map entire hydrological landscapes, identifying potential sites of water manipulation that would be impossible to see from the ground, offering a bird's-eye view of a forgotten battlefield. Beyond just identifying features, hydrological modeling takes this understanding a step further. Once these ancient networks of channels and earthworks are mapped, scientists can use computer simulations to recreate the flow of water through them. They can input historical rainfall data, estimated river volumes, and the likely dimensions of medieval engineering structures to model how water would have moved across the landscape. This allows them to answer crucial questions. How quickly could a certain area be flooded? What would be the exact depth of the water? How long would it take to drain a diverted channel? These models can even simulate the impact of floodwaters on different types of terrain or structures, providing an almost real-time understanding of what a medieval engineer might have aimed to achieve. It's like having a digital time machine that lets us witness the strategic flooding of a plain or the careful management of a castle's moat system in action. Ground-penetrating radar, or GPR, is another invaluable technique, especially for uncovering what lies beneath the surface. While LiDAR reveals the overall topography, GPR sends radar pulses into the ground and measures the reflections, allowing archaeologists to detect buried structures like the foundations of a sluice gate, the compacted earth of an ancient dam, or even filled-in channels. This is particularly useful in areas where subsequent construction or agricultural activity has obscured the original medieval landscape. Combined with traditional archaeological excavation, which provides detailed ground-level verification and artifact recovery, these technologies create a comprehensive picture. It's a true synergy where vast, remote surveys point to specific locations for targeted, precise digging, maximizing efficiency and discovery. The application of these techniques isn't just about academic curiosity. It has practical implications for understanding medieval warfare and engineering. By reconstructing these complex systems, we gain a deeper appreciation for the technical sophistication of medieval engineers who, with only rudimentary tools and manual labor, achieved feats that rival modern earth-moving projects. It also allows us to re-evaluate historical accounts, sometimes confirming the accuracy of old chroniclers and sometimes revealing discrepancies that lead to new interpretations. This bridge between the past and cutting-edge technology continues to unlock the hidden marvels of medieval water engineering, proving that the landscape itself can tell stories that written records sometimes miss, offering a tangible connection to the strategic minds of a bygone era. Beyond the sheer engineering marvels, the story of warfare by water reveals a profound human drama, a testament to both astonishing resilience and unimaginable suffering. For the soldiers tasked with defending a water-fortified stronghold, or those attempting to besiege one, life was often a brutal test of endurance. Imagine a medieval garrison cut off from fresh supplies by a meticulously planned river blockade, watching their water sources dwindle, knowing that disease from contaminated wells could be a far more deadly enemy than any attacking army. Their daily existence became a constant struggle against thirst, hunger, and the creeping dread of contagion. Their morale eroded not by direct combat, but by the slow, relentless pressure of hydrological deprivation. Their resilience was measured in their ability to endure these silent sieges. For the civilians caught in the crossfire of these watery campaigns, the impact was even more devastating. When entire landscapes were intentionally flooded to create defensive barriers, homes, farms, and livelihoods were obliterated in a matter of hours. Families who had lived on the same land for generations watched as their fields, their livestock, and often their very dwellings disappeared beneath the rising waters. This wasn't merely collateral damage. It was often a deliberate tactic, transforming productive land into an impassable, barren swamp to starve out a besieged city or halt an invading force. The suffering was immense as entire communities were displaced, left to wander as refugees, their survival dependent on the meager charity of others. Their resilience was in their ability to rebuild, to simply carry on after such catastrophic loss. Consider the human ingenuity involved in these desperate circumstances. When a city was under siege, with its primary water sources poisoned or diverted, the ingenuity of its inhabitants became their last defense. People would dig deep new wells within the castle walls, sometimes finding only brackish water, but enough to sustain them. They would meticulously collect rainwater in every available container, often risking their lives by venturing out during skirmishes to reach a hidden spring or well outside the immediate siege lines. Every drop became precious, and the ability to find or conserve water became as vital as any soldier's training. This creativity under pressure highlights the incredible human capacity for problem solving when faced with existential threats. Conversely, the psychological toll of water warfare was immense, affecting both sides of the conflict. For the attackers, advancing across a deliberately flooded plain was a nightmarish ordeal. Their heavy siege engines would sink into the mud, their horses would flounder, and their soldiers would be exhausted by the sheer effort of slogging through treacherous, waterlogged terrain. Such conditions bred disease, dampened spirits, and made every step a struggle against the environment itself, rather than just the enemy. The sight of vast, artificially created lakes stretching before them, seemingly endless and impassable, could demoralize even the most determined army, forcing them to abandon their offensive without a single arrow being fired. The human drama played out not just in pitched battles, but in the slow, agonizing grind of environmental manipulation. Even the engineers themselves were part of this human element, facing extraordinary challenges and often risking their lives. Imagine medieval hydraulic engineers equipped with only rudimentary tools, directing massive labor forces to divert rivers or build complex sluice gates under the constant threat of enemy attack or the unpredictable forces of nature. A miscalculation could lead to disaster, sweeping away workers or undermining an entire defensive structure. Their ingenuity was matched by their courage, often working at the very edge of the battlefield, making crucial strategic decisions in real time. Their success or failure directly translated into the suffering or salvation of thousands, blurring the lines between technical skill and battlefield heroism. These watery weapons were, at their core, wielded by and impacted deeply human hands and hearts. From defensive moats that guarded formidable castles to the deliberate, strategic flooding of vast landscapes, medieval engineers masterfully transformed rivers and other water bodies into formidable weapons. This profound understanding of hydrology didn't just shape individual battles, it profoundly influenced the entire course of warfare and determined the very fate of kingdoms. Throughout this journey, we've explored their ingenious strategies, revealing in detail how a deep, intuitive grasp of water's power became an indispensable cornerstone of medieval military might. It's a powerful narrative of human ingenuity and adaptation. This remarkable legacy reminds us that true innovation, even when constrained by what appear to be rudimentary tools and limited technology, can transcend the boundaries of its own era. The principles these engineers discovered and applied, born out of necessity and brilliant observation, continue to resonate deeply, influencing even modern strategic thinking in ways we might not immediately recognize. It is a testament to the fact that the mastery of nature, bending its immense forces to human will, remains a powerful, often subtle, and endlessly fascinating force in conflict. Take a moment to reflect on how our ancestors, with a blend of practical knowledge and sheer determination, harnessed the very elements that surrounded them. They didn't just build defenses, they reimagined the battlefield itself. Consider the enduring, almost timeless power of water, an element so fundamental to life, yet also capable of immense destruction, as we continue to shape our world and navigate its challenges. The lessons from these medieval hydrological conflicts offer a unique window into humanity's continuous interplay with the natural